All right, great. So thank you for joining for everyone who's watching right now. This is an exciting time to be in the cloud. We got just so many great technologies. Kevin, great. Kevin, I just want to let you know your whole screen is sharing. So if that was intentional, that's great.
Yep, thanks, Jonathan. What do you need?
I want to hear him, but I don't want to.
Headphones.
Go. Oh, you know what I'm going to do, actually? Yeah, exactly. I need to get him. All right. Hey, Kevin, are you there?
Yep.
Perfect. All right, so I am going to. Great. Kevin, you there? You still there, or you went to sleep?
I went to sleep.
Well, hey, look, Kevin, thank you so much for joining this online meetup. I'm very appreciative of this. I know your knowledge is just, you know a lot about big data. You come from a very extensive background. So maybe just do a quick introduction of yourself and your background, and we'll get started. And thank you everyone for joining the online meetup. We're excited to have you. Hopefully you have questions, because that's where the real benefit is of these online meetups, is to have that interaction. So I'm Jonathan Cham. I know I've posted most of these, but yeah, Kevin, please introduce yourself.
Thanks, Jonathan. My name is Kevin Tsai. I am a big data machine learning specialist in the GCP team. So I work pretty closely with Jonathan. And I actually joined Google not too long ago, around October of last year. But before that, I was at Microsoft. I pretty much did the same thing around big data machine learning as well. My data background goes back to the relational data warehouse days. So I'm kind of dating myself here a little bit. So I think I'll stop there.
You're like, what, 70, 60?
Thank you very much.
No, but you look much younger than that. So
really, look about 59, right?
Yeah. So I mean, BigQuery has just been, one of our kind of staple platforms here at Google. There's really nothing like it. All my customers ask about it. Why? I guess at a high level, what made you interested in working with BigQuery?
Yeah, it is definitely a different animal. I actually read about it in a paper probably about maybe 3 years ago. The journal paper. I mean, I think journal paper came out in 2010, right. And what was pretty interesting was how this was a service. It was actually a homegrown service, right? I mean,
yeah.
the original problem that Google had was the amount of logs that it created. And so there was a very smart engineer that kind of said, hey, I kind of want to do this a little more interactively instead of just sitting here, right? So he put together the earlier version. Internally, it's called Dremel, right? And it's like almost everything else at Google, it's one layer building on top of another massive layer, right? So it runs on top of our which I'll talk about a little bit later. Jupyter Network, Colossus storage, and so forth. And it's serverless, which is pretty interesting, right? So if you want to go ahead and do most big data type workload, you pretty much have to spin up a Hadoop cluster, right? And your cluster is running. On-prem, you pretty much don't have a choice, but in the cloud, it's really nice to be able to have a big job, issue the job, right? And then let it run and let it scale to really massive scale. We're talking about equivalent of thousands of cores, right? And once the job is done, then the cores are decommissioned, right? So so you don't have to manage the cluster at all. So you kind of think of it as true platform as a service, right? So that's pretty interesting, and just the scale of it is very exciting. And I'll also give an example of an area where BigQuery is very strong at, which I don't really see it being used very much publicly, which is around using BigQuery not just as a query engine, but more as a data processing engine. So that part is pretty exciting as
That's
well.
cool. That's cool. Yeah, I know you have some demos and slides, so we'll kind of just let you get started. But I have to ask you, what is a Kimball warehouse? And I'm a dummy, right? I don't know what that is.
No. It's not dummy. It's just it dates you. It dates me. Doesn't date you, right?
Oh, okay. All right. Yeah.
Yeah. So back, you know, data warehousing, has gone through many years of, I guess, iterations, and for, there were like a lot of known problems like stovepiping and other data management issues that kind of propped up probably maybe about 20 years ago, about 15, 20 years ago. And then there are two gentlemen, one by the name of Bill Inman and one Ralph Kimball, that came up with their methodologies that have become pretty staple practices, right? And I think one of the things that we'll try to do in this deck is to apply some of those strategies, which historically has been really made for relational databases. But apply it to BigQuery because even though the technology has changed, the business problems around data management really hasn't. So eventually we will have to have some kind of methodology practices, even with BigQuery or Hadoop or Hive, that will help customers manage their data.
Okay. No, that's interesting. I didn't know that. Yeah. So that's a good background. So let's just get started. And for those listening, make sure to have questions. And we have the smartest person on BigQuery here. So don't definitely take advantage of that.
I will make the slides available too. I think somebody asked for that.
Oh, perfect. Yep.
Yeah. So one of the beautiful things about working at Google is how open we are internally. So Jonathan and I, for example, are privy to a lot of internal information. So one of the things that we had to make sure about for this presentation was to do a bunch of Google search to make sure all the information is publicly available, and it is. Right, and the other part is some of these recommendations around using Kimball warehousing in BigQuery is really not official Google advice, at least not yet. So please take this as a lot of the information you get from this talk as a work in progress. So the agenda today, we'll go ahead and talk about where BQ fits within the Google Cloud Platform. We'll go and dive down a little bit around the architecture of BQ. This is kind of important, especially if you're coming from a relational side, because the performance characteristics of an engine like BQ is not the same as a relational engine. And this is going to shape how you're going to write queries to maximize performance. And we'll go through some examples using some of the queries. They're very simple queries, right? Nothing very crazy. But we'll walk you through how to look at query explanation to see what's going on under the hood to kind of show you, what we kind of talked about with an architecture part. We'll touch a little bit about Kimball. Kimball is a very big topic, but we'll touch about some of the key aspects of Kimball and how we could apply that with BigQuery. And then, as I mentioned earlier, I'll give you an example of how BQ could be used as a generalized big data processing platform. And I think Jonathan and I can wrap up with what are the upcoming meetups, which are pretty exciting. I see that on the list already. All right, so this is the data components slide for the components within GCP. So if you see, the slide's really designed to go from ingestion to consumption. And if you see, BigQuery is really tagged in the storage and the analyze area. Now, if you come from a more traditional data warehouse background, then you can kind of think of BigQuery as your both your operational data store as well as the presentation layer data warehouse. So you'll still use familiar technologies like Tableau and MicroStrategy on the client side to consume the data. And you're probably using some kind of ETL process that you have right now to massage the data if you're using it as an ODS store as well, right? So what makes BQ fast?
Hey, Kevin, do you mind if I ask you to do full screen, or is there a reason
Oh,
why?
sure.
Yeah.
So
Yeah, I think it was a little hard to see on the previous slide, but I mean, because that's a really good slide that shows exactly the architecture of how our customers ingest data and how it gets pulled into BigQuery.
I apologize, Jonathan. I'm actually kind of like 3 months new into, because I've never used. By the way, Google G Suite is like amazing, right? It's amazing. It's amazing for collaboration. It's just what a great platform. For many years, I've never used this before, but I guess how do I go to full screen?
You just go to present, I think. Yeah, just press the present button. I don't think it gets any easier than that.
Oh, this guy right here.
I think so. There you go. All right. And then if you want to, it says press escape to exit. Yeah, so that just shows you how much Kevin knows about anything else except big data.
Oh, great. What a great host. It is a fantastic tool for collaboration. I'm really impressed by G Suite, gotta say. Anyway, so what makes BQ fast, right? If you kind of think about any kind of data warehouse or database, you're gonna have your hardware components like your storage, your compute, your network, and so forth, right? Now, as with a lot of things in Google, what we actually do in Google is, our data center offer services kind of like in layers. So Colossus is our distributed storage with many, many, many thousands of disks in one huge cluster at data center scale. We're talking about, right? We're not talking about like a rack of like EMC or something like that, right? We're talking about a data center scale distributed processing where I could go ahead and store a file and it automatically the file itself will get shredded into thousands of drives. So I could take advantage of the performance of all these different spindles simultaneously, right? So that's Colossus, and Colossus replaced GFS. So a lot of you probably are familiar with the white paper GFS. That's one of the two white papers that created that Doug Cutting took when he was Yahoo to create Hadoop, right? So we've gone past GFS and now we're at Colossus. Borg is our server resource management, cluster resource management. So I'm sure a lot of you probably have heard of Kubernetes. So Kubernetes is an open source version of Borg, right? So the nodes that run BQ are managed by Borg. And then finally, tying all that together is Jupyter. Jupyter is pretty interesting. There's actually a pretty interesting story I've included in the link at the end, where as you may know, Google's pretty tight-lipped about a lot of these development until we write a paper. So back in 2012, before we wrote a paper, nobody really knew what Jupyter was, and it's built on top of our switches, and it's called Pluto. And apparently, the story is that a box of these Pluto switches got sent incorrectly to a different recipient who's not Google. And so this person, the IT person kind of wrote on a blog saying, hey, we just got, a set of Pluto switches. Do you know what this is? And it's almost like it was some hardware that came from outer space that nobody's ever seen, right? And people are kind of deciphering. It was pretty interesting. But but just to give you a scale what Jupyter could do is that think about 10,000 servers being able to talk to one another, any node to any node, at 10 gigabits per second, right? So we're talking about across all the nodes where this switch has a capacity of 1 petabit per second. Actually, it's now we have a paper that talks about how it's at 1.3, and now it's even higher, right? So just imagine being able to copy 125 or 150 1 terabyte drives in 1 second. So that's the capacity of this switch. Google went ahead and created our own switch technology because even years ago we anticipated that commercial technology would, number one, not be sufficient, number two, be way too expensive, right, for the scalability that we needed. So these are the three underlying components to BQ. These are also shared services that other components within GCP uses as well. Now within BQ, there are a couple of very critical pieces. One is capacitor. The previous name to this was column IO, and so as you can imagine, BQ is a columnar engine, meaning that each data file, when you read into the BQ format, is actually stored in columns. So what that would mean is when you go ahead and write a query, for example, and you're only querying columns 1, 3, and 14, then we're not going to go ahead and read all the other columns as well. And this is pretty standard for column-style databases, right? But what's special about capacitor is that behind the scenes we actually run statistics on the data, and we massage the data transparently to optimize for the shape and the distribution of the data within those chunks as well, right? So that's something that we actively do in BQ to help you optimize the performance. And then Dremel is the kind of the execution engine sitting on top of all that. And I think I have a few slides to kind of go through to explain that.
Yeah, I mean, you have a lot of content, so we might want to kind of move a little bit quicker. But I mean, just to summarize what Kevin just said, I mean, I was kind of amazed that we built all these technologies at Google because there was no one else or nothing else that could support. I mean, we have 1 billion users on Gmail and 8 billion across 8 different apps. I mean, that's a lot of logs and data, and just that's just a lot of information to manage. And we had to build all of that internally and build our own hardware to support all of this. And this is kind of the great thing about, we're pretty much just externalizing what we've built internally to our customers so that we can leverage our platforms here at Google.
Right. Great point. Yeah, Jonathan, I feel really privileged being here because I remember like there was a quote that Doug Cutting created Hadoop when he was at Yahoo, right? I think he said something like, Google lives a few years ahead of the rest of us, and at times send us messages.
Yeah.
Pretty funny. Yeah, but anyway, so okay, so for if you've done MapReduce styles type of queries, like maybe through Hive or something like that, this might be a little familiar for you. But then if you're coming from a relational side, I just kind of want to go through a few of these slides to kind of show you how BigQuery and does these queries and joins, right? So this is pretty typical whether you're doing relational or BigQuery / Hive style of query. Is when you're just doing a where clause, what just happens is that where clause it's a predicate push down to all the nodes that are processing the data, right? So that's pretty straightforward. It's in Spark, if you use Spark, in Spark's terminology, this would be a narrow transform because you're not shuffling any data, right? So this is pretty straightforward. And I'll give you an example where BigQuery could do this very, very, very fast, right? Now, what about a shuffle? Now, when it comes to BigQuery or Hive or Spark, when you think about a join, right, it's really based on a shuffle, right? And so let's kind of go through a shuffle, right? So in this case, we have to have the mindset that, hey, my data is a big data. It's not like tiny data. Tiny data, you could shuffle within the same node, right? The idea about big data is your data is so big that I'm going to have a shard of data here, a shard of data there. How do I go ahead and make it so that I could actually do the shuffle properly, even if one node cannot handle the whole data set, right? So, I mean, the idea would be to just look at the key you're shuffling on and you push it to a destination location. So have all your shards, your originating shards, push its portion of keys of that key to the same shard at the end. So in this case, what we're doing is we're shuffling by animal, right? Now, there is, as you can see over here, there is a risk of ending up with shards that are uneven, right? So you have a distribution problem, and what BigQuery does is that it does a bunch of repartitioning under the hood to help you balance out this type of imbalance. And we'll talk a little more about that when we look at the execution plans. Now, a shuffle join is when you have two tables that you're actually joining together, right? So in this case, we have a table of users and a table of, actually, the second table is actually a recommendation table. So basically, if a user is a cat person, what do you recommend, that person to buy? If a user is a dog person, what do you recommend the person to buy, right? That's basically what this is. So what we're doing is we're just joining the user table with the recommendation table, right? So in this case, what we're doing is we're shipping all the cats, from both tables, right, to shard 1 on the top right. And then we're going to go ahead and do the same for dog in shard 2. And once the keys kind of get collected, you're going to go ahead and have your output tuples, right? So basically, what you're saying is, Abby, let's recommend cookie fillet, and I ran out. I'm not a dog or cat person. I don't have any animals, so I just made it up. So I don't know why I put spider for dog. Maybe dogs love to step on spider or something like that. So this is how we actually do a join, right? So if you come from a relational database engine, the join process is kind of different until you get to the end, right? When you get to the end, especially when you're putting two tables together, then you'll probably do some, especially when they're big tables, right? You'll probably be doing some kind of hash join. That's what this really is. Now, as you can see over here, though, both tables are getting shuffled, right? So you could see this, all these arrows right here, would be pretty expensive in terms of networking. And, we ride on top of Jupyter, which allows us to have very fast performance. But still, if you could avoid having this type of shuffle, it's going to be better performance anyway, right? So one of the optimizations that we see in BigQuery is called a broadcast join. So if the output of the second table of one of the tables, or if the data set of one of the tables are small enough to fit in 8 megabytes, and it's compressed 8 megabytes, so the original size would be bigger than 8 megabytes, right? If after compression, it can fit inside 8 megabytes, then this 8 megabyte chunk would get just copied to all the other nodes, right? So then what happens is, in this case, you're gonna go ahead and have this cat dog. And so I'm using an example where it's much smaller, right? Just two rows. Gets shipped to shard 1 and shard 2, and then the local join happens over there. So the advantage is, if you have one very, 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 very big table, right? And you don't want to have a lot of data movement on that by doing all the different, repartitioning and the sorting. Then using the broadcast join, what BQ would do is it will keep those shards in place and just send the tiny shard across the wire, right? Which would reduce in your network time. Okay. So this is a schematic on the architecture of how a Dremel job happens through its pipeline. And this is Dremel, not the current Dremel, right? I'll have another slide right after this on the current Dremel. But up until the last issue, Dremel 9, we had this kind of pyramid style, topology. And this works very well. And remember, we talked about how the original reason for BQ was for Dremel was to do log analytics. So it would make a lot of sense that the raw data is very, very big. We're talking about hundreds of terabytes in size, and then each time when the query runs, so each stage of the data gets smaller and smaller and smaller until you hit maybe it's like how many % of the log records are failures, something like that, right? So the actual answer is going to be very, very tiny. Now that's not necessarily the case when you do joins. When you do joins, your intermediate data could actually have an explosion, as we saw earlier, right? So even though you could have a triangular structure of data going, the query going down by doing push down, that's the easy part. Coming back up might not be triangular, right? It could be, in this case, like this, it's hexagon, right? It's not. No, it's pentagon, right? It's pentagon, right?
Yeah, it's okay. You don't need to know your shapes.
Well, I didn't want to. I thought it didn't sound like a pentagram. I guess pentagram would be kind of satanic, right? Yeah, so it could be a pentagon, right? Because the data coming up through phases of joins could actually explode, right? So so we need some structure that's a little more flexible. So in Dremel X, we have this structure where the number of workers at each stage could be on demand different, and BigQuery is responsible for doing all the rebalancing. I think earlier I kind of talked about how you can actually have skew, where the output of one shard could be a lot bigger than the output of another shard just because of queue distributions, right? So with Dremel X, BigQuery would actually go ahead and do that repartitioning for you behind the scenes to help you rebalance. And the outcome of that would be you might end up with certain worker nodes being, more worker nodes working on a certain key versus another to balance out that performance. Because what you don't want to end up with is, in all distributed systems, is you don't want to end up with one of the nodes carrying so much load that becomes the straggler when all the other nodes are done with their job, but you're still waiting on this one, right? So this kind of allows us to help minimize that kind of impact. All right, so let me go ahead and go through some queries really quickly. These are really simple queries, all right?
Yeah, demo is nice. I like these demos. I think before, you might talk about this later, but what is a good set of data? Like, what are good cases for using BigQuery? Like, how does your data, how should it be structured? Is there any kind of limitations on, the data that should be in BigQuery?
That's a good question, Jonathan. One of the general recommendations is to denormalize, right? We always tell our customers that, denormalize, but it's actually possible that the customer's data schema is in a way where if you denormalize everything, then you're gonna end up with a table that's got 1,000 columns, right? And that could get kind of expensive in terms of storage. So you might end up with partial denormalization. And I'll have an example of that. I'll talk a little bit about that later on, right? In terms of actual size, if you shouldn't have to worry about number of columns or number of or the size of the table itself, right? Because when you actually query, you usually only want to query a subset of columns, right? So when you query those subset of columns, BQ would only go against those column data, right? All the other columns that are not called by your query will not be touched. And that's pretty similar to, it's pretty common practice for column databases to do that, right? And I do have an example later on about partitioning. So if you could partition your data by day, then you could also use descriptors in your query to do partition pruning so that you don't, so BigQuery will know which partitions to look at and thereby not look at all the other partitions, right?
Right. Right.
And that kind of helps with, especially with time series data, especially time series data, right? Like a transaction fact table.
Yeah. I think one thing I realized as I was evaluating BigQuery was that, I mean, it's very simple to use, right? You literally just have, you can have denormalized data. There's no indexing. There's no management of your data. You just kind of tell BigQuery what the schema looks like, throw it into a bucket, and then write your SQL query. So it kind of takes out all the management of, kind of separating your tables, creating just basic, there's no management of data. You just throw it all in there, run your query, and let BigQuery kind of figure out how to spin up the thousands of cores it needs to do the analysis and give you the results.
Yeah, that's so yes, so that's great. That's a great point. I didn't talk about. You don't have to create indexes, right? I mean, there's really no chance for you to. You cannot create indexes in BigQuery. So it's not like a regular relational database where you have to select one order, natural order for the table, right? And then there might be secondary indexes that you create, and if it's a partition table, then those indexes generally cannot be unique. And then now you're talking about index management on top of all that. So what relational databases, I mean, that's very good for a relational database if you're doing, let's just say, seeks. If I want to have, my result set is a very small result set, and I'm just, going to return maybe 10 records, then seeking those indexes would be very, very fast. But anytime you do aggregation across a segment of rows, you kind of end up with doing a table scan anyway in those engines, right? And so what BigQuery does is that it just does a scan anyway. You just do a scan, right? And so you can come from any direction, with any predicate, and you have pretty predictable experience, whether you're going against your predicate is on the first name column or the last name column or the age column or whatever column, right? Because you're just doing a scan, right? And then when it comes to, let's just say, sometimes in an unusual case, you might have fact table to fact table joins, and that is something that relational databases, especially the scale out ones, start to fall over because it wasn't designed to do things like that, right? Whereas in BigQuery, we could easily go ahead and join two tables. Doesn't matter if we have no concept, of whether it's a dimension table or a fact table, right? You just join the two tables together. Just join it, So so Jonathan, it kind of simplifies things, but on the other hand, I think I've kind of come from a relational side myself too. It's really a lot. There's a lot of getting used to, right? To see how could I now this new tool, right? So I'm going from a piston engine to a jet engine, right? So I mean, I have to think of it differently, right? All right, so I'm going to go through a few of these very, very, very simple queries, right? So this one is just a where clause, right? That's all it is. It's just a where clause. It's pretty quick, right? And I should probably do the uncache this. Now, you got to think about BigQuery as a locomotive as opposed to like a Ducati, right? So a Ducati would get you from one place to another really, really quickly. You just hop on the bike and you go, right? But you can only carry like at most two people. Locomotive takes a little bit longer to start up, so there is some like startup time in setting up the job and distributing the pushing down the queries. But once it starts running, then BQ has a very, very high throughput, right? So sometimes when you're doing tiny queries, it might still take 2 seconds, whereas if you run it on, let's say, an Oracle database or a SQL server, it'll be, oh, this query would come back really quickly. But then if you're doing it on, let's just say, tens or hundreds of terabytes, in BigQuery, it'll still be very fast. But then, those relational engines would start slowing down, getting bogged down. Right?
Right. So I think one good thing to say is you shouldn't use BigQuery for transactional information.
Yeah. Yes, exactly. So for that we have Cloud SQL, right? And a number of other different options. All right, so this is what it kind of looks like. All right, so these are the two stages. You can see that the table itself has about 160,000 rows. The output in this particular stage is only 5. So what has happened over here is that the where clause got pushed down to the actual lowest level leaf node, right? And then it executed a limit 5. We can kind of guess that only one node was executing because the output at the stage are 5 records, and that's it, right? And then the next stage is just reading it from the output of this and putting it into our result set, right? Now, if we go to another query, let's see. I'll go ahead and run this guy. All right, what is this? Okay, so basically what this is we are running this a group by query, all right, and let's see. Okay, we're grouping by corpus on word count, right? So this table actually has a word count column, a number of words, and also let's take a look at the explanation here. That's the exciting part. So in this particular case, what we're doing is we want to do corpus and some word count, right? So when we look at the actual base table itself, we're actually going to see 42 different titles, right, in the work of Shakespeare. And after that, what we're doing is we're doing a limit 5. So we're taking the top 5, right? And again, there's an output. So again, this is still another narrow transform. We don't have any kind of shuffle going on at this point in time. All right. And this is a big query, right? All right, so this is applying the BigQuery. Let's take a look at this. And we're running it. Okay, so this one is a little bit more interesting, all right? Because the data set itself is much, much bigger, as you can see over here, there are actually multiple stages that are going on. The source data has about 67 million records, and the output of this, is, you have 12 point something million records in an intermediate data set, right? Now, before coming down to the result, which is we wanted the top 5 records, right? There is an intermediate stage right before that generated 75 records. We could probably take a guess, right, that there were that a number of nodes times 5, right? Remember, the output of each of the nodes over here has 5 records, right? Yielded 75, right? So what do you have over here? So you have roughly about 15 nodes running, right? Something like that, or 15 shards running, right? So 15 shards generated 75, because what we're doing over here is because when you do a limit 5, you have to generate 5 records from each shard, because it is possible that a particular shard has the 5 highest records, right? And it's the last shard that actually end up deciding which are the 5 records to give back to you, right? And let's take a look at this guy. All right, so this is a join, and this join query is a shuffle join, all right? So as you can see over here, oops, it's cached. Anyway, it's fine, I'll just use cache information. As you see over here, the first stage is a read from this table, which is Wikipedia, and we're reading about 313 million records. The second stage is also a read, but it's reading from a different table, the inner table, right, which is Shakespeare, right? And then there's an intermediate result as well. So what the first stage and the second and third stage, right, which corresponds to the second table, stages 2 and 3 shuffles the data, and stage 1 shuffles the data as well, right? So that's kind of like that slide that we talked about where we have both tables shuffling into the same bucket. And then the stage 4 reads from that shuffled bucket and actually does the hash join over here, right? So as you can see, in this process, we are actually reading this large table twice, right? Because of the shuffle. Now, in this case, in the next case, we have what's called a broadcast join. So those are the same tables, right? The Shakespeare and the Wikipedia table, right? I think my cache is off, but it doesn't really matter.
Hey, Kevin, so while that's running, we had a couple questions. Ron was asking about, in one of your previous queries, was the query selecting capitalized words?
Yes, there was that's correct, yes.
Okay.
That is the one where there was a regular expression, that's correct.
Okay,
yes.
Cool. And then another question about, if you're joining two really large tables and there's no workaround to reorganize the data, I guess, how do we address kind of these type of queries, or do we just let, the compute do, take its time to do the joins?
Yeah, so, a couple of ways. I mean, one is to let it join, and I would kind of go back to, what are the requirements, right? What are the requirements from your experience perspective? Is this like a backend process where waiting is fine, right? If is a backend process where waiting is fine, then maybe we just go ahead and just let the join happen, right? But if this is a front end process that that could affect the customer experience, right, or your end user experience, then we definitely do want to take a look to see whether or not you could denormalize your schema, so that it's almost like a pre-query, right? So that your customers can have very fast experience. Because what BigQ does really well is on really large tables, but kind of like a flat schema.
Yeah.
Right?
So I've had customers, I know Roderick was saying that there's no workaround, but I found that when customers say there's no workaround, it's just the workarounds that are possible, they don't want to do, or it takes time to do it. But there's usually ways to split up the data set and flatten it out and denormalize it in a way that helps to optimize the query. And there's actually a link to BigQuery best practices that I'll send out to the chat room that that kind of talks about how to structure the data if you're doing specific joins.
Right.
Yeah. So.
Yeah, I mean, it's kind of in a way, it's kind of a case by case, decision, right? Because if it is crucial to have good like response time, right? Then we really need to start thinking about denormalizing that. Right? But good question. I mean, that's something definitely that comes up, quite often. Okay, so this is a broadcast join, all right, and I think I wanted to look at the explain part, which how is that different? So again, we're going to go ahead and read, right, from one of the tables. That's the Shakespeare table, and we're going to go ahead and arrange that, all right. But what we're actually seeing over here is there's just a second read to the second table, right? And the second read to the second table happens when this stage actually reads both from the inner join, the result from the inner join, which is right here, right? The inner query, which is right here. And then this is the output of that, which is that small, under 8 megabyte packet, gets sent to all the different nodes. that are running the shard, the larger shard, right? So in this particular case, you're not going to experience that that shuffle of that big table. But so this works really well if you could have, you know, a one table that's much smaller than the other. And so this is, I just kind of threw this in because this is kind of interesting, right? So when you do go ahead and do a run, oops, actually I do want to go ahead and use cache. So you could see, I mean, this is by no means the highest speed that, you know, we've seen BigQuery perform at, but this is a very simple query, right? What we're actually doing is we're just looking for this particular phrase within the text field content or string field content across the entire corpus. So what we've done is, you know, roughly about 20 seconds, we scan through about almost 2 terabytes. Right, so that's a pretty good scan rate. It's almost like 100 gigabytes per second, roughly about, you know, if you think about it, right, about if your spinning disk are about maybe 100 megabytes per second, then you had equivalent of 1,000 hard drives running for you in that query, right? So this is the power that comes from Colossus, right, the storage. And yeah, I also wanted to show you a little bit. This is how you would actually use partitioning. So in this particular case, this is a log data that comes from the Apache web logs from NASA during, you know, like 20 years ago. It's 20-year-old web logs, right? And what we're doing over here is we are constraining the partitions, and you know, it's just a period by period. So this query would be equivalent to something like, give me the sales figure for Q3 of 2016 versus a sales figure of Q3 in 2015, right? So this is period to period comparison. Oh, did we just lose the audio?
No, I can hear you fine, Kevin, but just a heads up, we have about 14 minutes left.
Got it. Okay. All right. So real quick. All right. So anyway, that's kind of like the quick walkthrough. Now, all right. Data warehousing. For those of you who remember this, then maybe you could kind of remember maybe this. I got this little posting, you know, from one of my friends on Facebook, you know, that basically says, you know, when people in their 20s are talking about old people, I mean, I guess they're talking about me now. Right? So if you know data warehousing, then you know, with Kimball and Inmon, then you probably kind of go a little bit farther back. Now, what we do want to do here is just kind of quickly talk about how can we implement some of these strategies for BQ, right? Because the technologies change from time to time, right? But the need for business, you know, or data management really doesn't change for a long time, right? So these are pretty timeless strategies. So just real quick, for those of you who may not know Kimball, so Kimball is known for the bus matrix, where it allows you to create the data warehouse kind of, you know, on an ongoing basis, as opposed to a very top-down method like Inmon, where you start with a enterprise schema. So you could potentially have your data warehouse created first in, I don't know, maybe store inventory or something like that, or retail sales, right? So your retail sales right down here, right in the middle, that might be the first data mart that you're creating. And as you create the data mart, then you'll create the dimensions. But you create the dimensions in a way that could be reused, so that when other business processes come in, they could use the same date and product dimensions. And if those new business processes come in with dimensions that are not created yet, then at that point of time, those dimensions are then created and put into kind of like a corporate standard enterprise matrix of dimensions, right? So what this does is it allows you to do things like profitability. So profitability requires you to have revenue minus a whole bunch of operational expenses. And if you want to do, let's say, profitability by customer, then you got to make sure that every single piece of data point will be able to be, you know, defined by the same way you define a customer. Right? So those methodologies work pretty well for relational, and so if you're, the slide basically kind of like recaps on, when we're doing, let's say, MPP type data warehousing, you're splitting on the fact and you're partitioning on the fact and you're replicating the dimensions, right? So this works generally pretty well unless you have edge cases, right? So for example, if you are if you're running a internet scale user dimension, right? If you have, let's say, 100 million, rows in your user table, then this type of methodology becomes a little bit less friendly, right? Or if your product dimension, that's another one that could be, potentially have a huge explosion as well, right? Now, so how do we do this in BQ? One edge, all right, so one end of the spectrum is just go ahead and just apply, the Kimmel method, as is. Just use a star schema and that's it, right? Now, it's again, this, is this the right way of doing it? It's probably going to be your least expensive in terms of storage, but it would probably be the riskiest in terms of performance. But depending on your SLA, that's and expectations with the customer, and maybe your data set is fine with that. Maybe you're always going to have broadcast joins, right? Just by the nature of your data, maybe this might be fine, all right? So just test it out, but make sure that when you do test, don't just test on a subset, test on a full data set, right? Because the full data set will potentially have all of a sudden push you from, let's say, a broadcast join into a shuffle join, right? And then the performance characteristic could be quite different. Again, like with typical data warehousing strategies, we heavily use views to hide the underlying physical schema, right? Now, on the other end of the spectrum, we have denormalize all, right? That's typically what you hear from Google, just denormalize, right? It is going to be the most expensive in terms of storage, and it will pretty much be a guarantee that it will be the fastest performing as well, right? So if you can, afford to denormalize, then by all means denormalize, especially when it's when your customer experience is very important, which generally speaking, for a lot of data warehouses, you're serving your users, right? So you want your users to be happy. Now, what's important though is even though you're denormalizing, meaning that a lot of the attributes coming from your dimension tables will now go into your fact table, you still want to model your dimensions as if you were not denormalizing, because dimensions kind of live separately. And even though I'm denormalizing this particular fact table, I might not denormalize the same attributes from the user dimension, for example, into a different fact table. So I want to keep my dimension tables pretty static. I mean, the schema of that pretty static. Right? And then with some practice, you might want to look at denormalizing. We call it denormalize sum, right? Which is find out which attributes that get queried very frequently, right? And you could usually do that by monitoring the queries that are coming in, right? And there will generally be quite a few, within a dimension table, there will be quite a few attributes that are always going to be queried, and you'll have most of the other attributes that are not queried at all, right? So those are the ones that you probably want to leave out of the fact table and promote the ones that get, queried often into the actual fact table itself. And again, really, in this case, you really should be using a view to hide underlying schema. So that'll give you the flexibility of promoting and demoting attributes into and out of the fact tables. Right. So this is kind of like an example. So imagine you have this person named Dakota, right? Last name North, lives in North Dakota. And so on a certain date, she moves to a different state, right? South Dakota. So what what should you do? Should you just go ahead and change the state from ND to SD, right? From North Dakota to South Dakota? Now you kind of think about what happens, right? From a historical aggregate perspective, if this person has purchased a lot of items in the past while she was living in North Dakota, when you do a query based on, let's just say based on by state, right? Sales by state. And if you just force her state to change from North Dakota to South Dakota, what actually happens is all the previous purchases that she made while she lived in North Dakota will now show up in South Dakota, right? And we don't want that. We want to have historical data be kept intact, right? And that's where, you know, one of Kimball's very popular methods, slowly changing dimension type 2, comes in, is that instead of just forcing a change on the state attribute from North Dakota to South Dakota, is that you put a second row and you put a start date, end date to it, right? And what's important is that you stitch this together. The user ID is actually what's called the business key. So this is this doesn't change, right? So this basically tells you it's the same person. And what in Kimball warehousing we use a surrogate key, which basically identifies a second generation of this user to really be a different person, right? So in the future, when you go ahead and do a query based on state, you're going to end up with some of the purchases by this person while she was living in North Dakota getting aggregated into North Dakota, and some of the rest of the purchases that she made while she was in South Dakota will get aggregated in South Dakota, and that's exactly kind of what we want, right? Now, if we go ahead and let's just say that, you know, first name, last name, and state are attributes that get queried very, very commonly, right? So what we would do when we go ahead and do this optimization strategy is to promote this into the fact table. So this is a fact table, right? So it actually lists, you know, the amount purchased and product key and so forth, right? So in this case, we go ahead and promote, you know, the user ID, which is a business key. We promote the first name, last name, and state into the actual fact table. Right, so this is when you create the view over this for the user to query, then the query by first name or last name or by state will no longer need to join the actual user table. Okay, so this is a method of, you know, enhancing the performance. But imagine if the user table has maybe 100, you know, or 200 columns, then you are selectively promoting these attributes into the fact table display. Right. Now, let's just say Dakota got married, and, you know, she married Bobby South, so her name got changed to South Dakota or Dakota South, and all it is you add a third row, right? And you add a third row with a new start date, right? And the previous row now has an end date, okay? And the user key remains the same because it is the same person, and this ties this person together. All right. And in this case, you know, any new records coming in that gets populated into the fact table will now have the new attributes, Dakota South. All right. Now, I don't think I think we're kind of getting up really close to time. So yeah, okay, this is good. So one of the optimization that you may want to consider is and this is something that I kind of thought about. How do we use something like nested rows, right? Because that's an optimization that we do have in BQ. Now, if you kind of think about, you know, tables that are very closely related, right? So in this particular case, we have this table which is a sales order table that have sales order lines. So sales order lines, there are multiple sales order lines in a sales order table. So this would be a great use case. This will basically allow you to have one free join, right? Without having to join these two tables together. You have kind of like, it's kind of hierarchical, right? So another one that might be useful would be, let's say, product category, right? And product subcategory. That's a hierarchy that you could use in the table like this. But then, you know, you kind of have to worry a little bit about, you know, the join syntax. It is kind of different, right? So that's something you might want to consider. Well, okay, I don't have enough time to kind of show you this, but I'll include this. There's the last page of the slide, so you can kind of take a look at this on your own. So I just want to give this. If there are any questions, no more questions. I just want to kind of give this back to Jonathan.
Yeah, I'm looking at. I don't see any other additional questions. I mean, I think that was great. It was deep, and you kind of gave some good best practices around using BigQuery. Maybe just to end it off with like some kind of high level, what have you seen with customers and in general, some high level best practices on going forward with BigQuery.
Yeah, so definitely, just in the few months I've been here, BigQuery has been used. At least, just the exposure I have with my customers is around data warehousing, and a lot of times they come to us after they try doing some data warehousing, and they try just doing a lift and shift of their Teradata or Oracle environment, right? And then they run into some performance issues, right? And that's really because of some of the things that we talked about that they didn't apply. I think you gotta have to look at BQ as a different animal and think of leveraging its strength, right? Because if you're just going to lift and shift something from a relational engine, you're not taking advantage of BQ strength, and you're really just using it in a way that it's not strong in, right? So I would definitely think of and try to understand how BQ works, because the queries that you write reflecting its strengths would be kind of different, right? The schema would be kind of different.
Yeah, I think BigQuery also like the first terabyte or some first X amount of query is free, right?
Yeah, it's the
Per
first
month.
terabyte. Correct.
Yeah,
Yeah.
first terabyte, which is awesome. I mean, it gives you a chance to play around with the product and lets you really uncover how BigQuery can do large data set analysis. We also have a lot of public data sets that you can play around with, which is kind of cool. I mean, I always do this demo where I'm doing a 100 million row analysis on Wikipedia. It took 2 seconds, and I asked, how would you do that with your existing system today? With SQL or whatever. And I mean, there's no good answer for that. But with this, it's just as easy as writing your query, pointing it to your data and pressing run. So I think that's what our customers really like about BigQuery.
Right. There's a couple of questions here. Do we have a limit or best practice on how many rows, columns? I have not run into that myself, because yeah, BQ is not like a relational engine where you have a page, a database page, and inside that page you carry all the rows. I guess in some column store you'll have you still have some kind of row store structure, but in BQ you don't really have that, right? So I can go. I'll take this as a question to see if there's any hard number, but I have not run into any hard numbers yet. I mean, we have this petabyte data set, right? I'll kind of even show you. Right here.
Yeah, we have a petabyte data set. So
petabyte data set, this guy right there, right? This table right here, is the table itself is 1 petabyte, 1.1 petabyte, right? And we've had people who just kind of did a select star from this query and got yelled at, right? Because we do get charged internally for using that, right?
Yeah.
And then the other question from Roderick is, are there any limitations on the node? I'll have to go ahead and find out. I have not read up on any kind of hard number on column, right?
And then did you answer Ron's question about comparing other data warehouse solutions to BQ? I mean.
Yeah, so if you're, okay, so structurally, I mean, we get a lot of queries around, we get a lot of requests around comparing Redshift to BQ, but the engines are actually pretty different, because Redshift is based on more of a relational engine. So it's kind of more like Teradata type, right? Where you have where you partition your fact table, and so and it's probably closer, structurally, it's probably closer to Hive, right? Hive on Tez or something like that. But again, you know, Hive doesn't have all the optimizations of going inside there to each of the shards and, you know, like massaging the order of the rows and stuff like that based on the distribution of data. I mean, that's something that what capacitor, which is a column part of, you know, of BQ does in the back end. So we're actually pretty heavy on, you know, doing all that stuff, right? And now, let's see. Gosh. Yeah, I'm not. So I know Roderick also has a question regarding mentioning that, you know, Impala and Parquet format would have some trouble joining more than a few hundred columns. I'm not sure, Roderick, if you mean that you are joining. Yeah, you actually have a join condition on a few hundred columns. Or is it because like your end result is like a few hundred columns? Because if the result says a few hundred columns, it shouldn't be a problem for BQ, right? I personally do not know of joining many columns together. Like, I mean, in the hundreds. What are some underlying data structures used to implement? I think I probably cannot answer this for sure. So I'll see whether or not I can answer. There's a question on, you know, whether it's written on C++ and, you know.
Yeah, I mean, I don't think we. Yeah,
Okay.
running in Java and C, and there's a lot of different code running, but you know, I don't think it's important for people to know what code it's written in. But yeah, what is the app on your? Well, what is TBS data? There's a question about TBS data.
TBS data.
Yeah, Vadim Barilko asked about how to load my TBS data. Are you familiar with that? It's okay. Let's go to Vadim. If you can clarify what that is, we'd appreciate it. And what is the app on your Mac, which is a green tube shape?
Green, this guy? This guy, right? Is it tube?
I think so. I think so. Yeah. What is that?
Yeah. So this is just this is just Navigator. So that's a Anaconda. It's just Python. Yeah.
Interesting questions you get.
Yeah. So Snowflake, no Snowflake, no Snowflake. So even when you're implementing Kimball warehousing on a regular relational system, he advises against snowflaking, mainly from a data management perspective. It is kind of true that, you know, during when you're doing your ETL process, that Snowflake is much more of a headache to manage than just a regular star schema. So we advise against it. Now, I mean, now if you're going to Snowflake it physically into BigQuery, then my goodness, then you're now having like multiple levels of table joins. So we definitely would not recommend that, right? So we should have these.
Yeah, I think we'll close it out now, Kevin. I know we're about 7 minutes after and your time is valuable. So I just want to thank everyone for joining. We'll send out the slides on the Meetup group, and just want to thank everyone for your time here. And thanks for the great questions. There were some really good questions in the chat today.
All right, thank you.
Yep, thank you, everyone. Goodbye.